Hi everyone, in today's video we're going to take a detailed look at the coupled pendulum system. If you have two oscillating pendulum interacting with each other via some kind of a spring system, let's suppose, then this kind of a system is known as a coupled pendulum system, and we are going to explore today what is going to be the general nature of its motion. How does the oscillations of one pendulum affect the oscillations of the other pendulum? How does the oscillations of the other pendulum affect the oscillations of the first? How do they interact with each other? What is the nature of their relationship? So we're going to look at the detailed nature of their motion in today's video. I'm going to do that by first applying the Lagrangian approach to obtain the equations of motion of the system. And once I obtain the equations of motion of the system, I'll try to solve them analytically to get a general solution. And once we obtain a general solution, we'll look at the peculiar properties hidden in the general solution. I will show you how there are two simple harmonic oscillations of different frequencies hidden in the general solution. And I'm going to look at the various peculiar behavior that this kind of a coupled pendulum demonstrates under certain conditions. And then finally, we're going to talk about what is known as normal modes and normal frequencies. So can this kind of a system execute SHM? Yes, they can under certain specific initial conditions. So we're going to take a look at the Lagrangian approach, the equations of motion, the general solution, the peculiar behavior of the general solution, and normal modes and normal frequencies. So let us explore the beautiful relationship that exists in a coupled pendulum system. Let us start. So we start with this kind of a schematic of a coupled pendulum system where let's suppose that you have a pendulum of length L and point mass m, and another pendulum of the same length L and point mass m interacting with each other via some kind of a spring mass system having spring constant k. Okay, so if I want to obtain the equations of motion of this kind of a system, and first of all, I need to obtain the Lagrangian. And to obtain the Lagrangian, we need to calculate what is going to be, let's suppose, the kinetic energy of the system. Okay, there are 2 point masses here. The first mass is attached to the first pendulum, the second mass attached to the second pendulum. So the kinetic energy expression for this kind of a system is simply given by half m v square, where v1 square rather for the first mass, and half m v2 square. However, we need to associate some kind of coordinates with this motion, right? We can do that using xy coordinates, but since this is a motion that is restricted to the plane, and we can use polar coordinates because the radial displacement is always constant, I'm simply going to use the angular displacement of each mass. The angular displacement of each mass is going to specify to us where the entire system is at any given point in time, because the length of the pendulum are fixed. So let's suppose the angular displacement of the first pendulum is θ1 and the angular displacement of the second pendulum is θ2. So if I'm interested in finding out the velocity v1 for the first pendulum, then you'll observe that the nature of its motion is along an arc. So along an arc, it has a particular velocity, let's suppose v1. Now you may know that if some kind of an object is undergoing some sort of a motion along the arc of a circle, then the velocity can simply be written by r omega, where r is the radial distance from the point with respect to which that kind of a circular motion is taking place, and omega is the angular velocity. So r here is L and omega here is nothing but θ1 dot. Dot simply meaning the time derivative of θ1, which is nothing but omega 1. So this is nothing but half m L θ1 dot square, right? Similarly, the kinetic energy for the second mass is half m L θ2 dot square, right? So this is the general kinetic energy expression for the entire system. Now I also need to obtain the potential energy expression, which is V. So the potential energy is mg times the height. Now I need to fix some kind of a reference associated with the zero potential. So let's suppose the level at which the pendulums are attached to the pivot, that level, that horizontal level, is the level for zero potential. So here I'm interested in finding out what is the instantaneous height from that level for the first mass. So because this is below level 0, I'm going to say this is minus mg, and the height is nothing but L cos theta 1. Similarly, for the second mass, it is mg, and the height, instantaneous height, is given by L cos theta 2, again minus because it is below the 0 potential reference. And there is also the potential energy because of the spring mass system. So potential energy because of the spring mass system is nothing but half k. Now I need to find the extension. So let's suppose that the general sort of a elongation of the spring mass system is 0. In that kind of a situation, the extension is basically given by what is the extension of the one end of the pendulum and the extension of the other end of the pendulum. So the extension of the one end is given by L sine theta 2, and the extension of the first end is given by L sine theta 1. So the overall extension of the system of the spring is basically L sine theta 2 minus L sine theta 1 whole square. This is the potential energy due to the spring mass system, right? So therefore, finally, we have the Lagrangian associated with this kind of a coupled pendulum system. The Lagrangian is simply given by L is equal to T minus phi. So T is nothing but half m L square theta 1 dot square plus half m L square theta 2 dot square, and the potential energy is minus phi. So this is plus mgl cos theta 1 plus mgl cos theta 2 minus half k L square. We have sine theta 2 minus sine theta 1 whole square. All right, so this is a Lagrangian of this kind of a coupled pendulum system. However, I'm interested in studying the nature of its motions where the angular displacements are small. So you see, I don't want this kind of erratic behavior. Actually, I am only interested in finding out the nature of its oscillations for the approximations of small angles. So if I make small angle approximations, in that case, I can substitute sine thetas with the theta. So for smaller angles, sine theta as a function varies in the same fashion that theta varies. And cos theta can be written as 1 minus theta square upon 2. So if we make this kind of a small angle approximation to the coupled pendulum system, then what is the nature of its Lagrangian? In that case, the Lagrangian becomes L is simply equal to half m L square theta 1 dot square plus half m L square theta 2 dot square plus m g L. You have 1 minus theta 1 square upon 2, and then you have plus m g L. You have 1 minus theta 2 square upon 2 minus half k L square. Here it simply becomes theta 2 minus theta 1 whole square. So the Lagrangian simplifies to half m L square theta 1 dot square plus half m L square theta 2 dot square. Now here I want to separate the theta 1 term, so that becomes minus half m gl theta 1 square, and from here I'll get minus half m gl theta 2 square. Let's keep the constants for the end of the expression, and then I'll get minus half k L square theta 2 minus theta 1 square, and the expressions corresponding to these constants are simply going to be plus mgl, which is 2mgl. So here it is, the Lagrangian of the coupled pendulum system under small angle approximations. Now once you obtain the Lagrangian of this kind of a system, the rest of the approach is very simple. What you do is you plug in the Lagrangian, which is a very important quantity, into what is known as the Euler-Lagrange equations of motion, and from there we will get equations of motion of this entire system. So I want to plug this into, let's suppose, what is the Euler equations. Since there are two variables here, I'll have to apply this first with respect to theta 1 and second with respect to theta 2. The first equation is d by dt upon del L upon del theta 1 dot minus del L upon del theta 1 is equal to 0. The second is d by dt upon del L upon del theta 2 dot minus del L upon del theta 2 is equal to 0. So if I want to represent the equation in terms of the Lagrangian, first I need to find the partial derivatives corresponding to these terms, right? So let us find out. So here del L upon del theta 1 is what? So if you look at the expression of Lagrangian, there are only two terms that contains theta 1, this one and this one, right? So del L upon del theta 1 should simply come out to be minus mgl theta 1 for the first term. And for the second term, you must have minus k L square theta 2 minus theta 1. And once you do derivative of theta 1, that becomes plus. Okay, this is for the second term. Similarly, you will have del L upon del theta 1 dot. So how many terms are there for theta 1 dot? This term is there. That's it. From here, you should get m L square theta 1 dot. And the time derivative of del L upon del theta 1 dot is equal to m L square theta 1 double dot. Similarly, let us also find the expressions for, let's suppose, del L upon del theta 2. So for del L upon del theta 2, you have this expression and this expression. So you should get two terms here. So the first term that you're going to get is minus m GL theta 1. This is what you're going to get. So for the next quantity, you will have del L upon del theta 2 dot, which is equal to, you're going to get this from here. This is ml square theta 2 dot, right? So ml square theta 2 dot, and for d by dt of del L upon del theta 2 dot, you will get ml square theta 2 double dot. So from here you can obtain the equations of motion. So let me plug all of this into this equation and into this equation, and then we will see what expressions we get. So the first equation becomes m L square theta 1 double dot minus, so minus minus becomes plus m GL theta 1 minus k L square theta 2 minus theta 1 is equal to 0. And for the second case, you have m L square theta 2 double dot minus minus becomes plus mgl theta 2 mgl theta 2 minus minus becomes plus kl square plus kl square. So we are almost there, guys. We are almost there. The equations of motion are just within our reach. I want to simplify this. Okay, so let us simplify the first equation by dividing the entire quantity by ml square. So if I divide the entire system by ml square, this simply becomes theta 1 double dot, right, plus here if I divide by ml square, this becomes g upon l theta 1, and this becomes k upon m theta 2 minus theta 1 is equal to 0. And in the second system, if I divide the entire system by ml square, this becomes theta 2 double dot, and this becomes g upon l theta 2. This becomes k upon m theta 2 minus theta 1 is equal to 0. So there you have it, the two equations of motion corresponding to both the masses in the coupled pendulum system. So in the coupled pendulum system, you had two masses, both of them attached to two pendulum as well as attached to a spring connecting each other, and their positions are basically given by the variables theta 1 and theta 2. So therefore, the motion is governed by these two equations, these two second order differential equations in terms of the unknown variables theta 1 and theta 2. So let's suppose this is equation number 1 and equation number 2. So now that we have obtained the equations of motion, the next challenge is to solve these equations of motion to obtain the general solution. Now, since these two equations of motion need to be solved simultaneously, what we can do is, if we are interested in analytically solving them, we can write both of these two equations in a compact matrix form. Now, please carefully look at the nature of these equations. If I want to write it in compact matrix form, let's suppose first I'll have a theta1 double dot and theta2 double dot. Okay, the first row will correspond to the first equation, second row will correspond to the second equation. Then what are the coefficients attached to theta1 double dot and theta2 double dot in both these two equations respectively? Well, in equation number 1, you have the coefficient of theta1 double dot is 1 and the coefficient of theta2 double dot is 0. In equation number 2, the coefficient of theta1 double dot is 0 and the coefficient of theta2 double dot is 1. Right? That's it. Next, I'm interested in finding out the coefficients corresponding to theta2 and theta1. So first I'll write theta1 and then I'll write theta2. So let me make it a little bit of a bigger matrix because I will have a lot of terms here. So what is the coefficient of theta1 in the first equation? So in the first equation, the coefficient of theta1 is here. First of all, you have g upon L, right? You have g upon L. And second of all, you have plus k upon m. So minus plus k upon m. So g upon L plus k upon m. What is the coefficient of theta2 in equation number 1? That is obvious from here, minus k upon m. Right. Similarly, what is the coefficient of theta1 in second equation? That is minus k upon m, right? And what is the coefficient of theta2 in the second equation? That is simply g upon L plus k upon m. Do you see that? Both these two second order differential equations therefore can be written in compact matrix form in this manner. So I can represent it much simply by saying that the equations of motion lead to m theta double dot plus k theta is equal to 0, where m is the matrix 1 0 0 1, k is the matrix g upon L plus k upon m minus k upon m minus k upon m, and g upon L plus k upon m, right? Theta double dot contains the second order derivatives of theta 1 and theta 2, and theta simply contains the solutions that we are interested in, theta 1 and theta 2. So all we are interested in is solving this compact matrix form of an equation that contains two simultaneous second order differential equations. Now, some of you may have actually seen differential equations that look like this. Some coefficient multiplied by the second order derivative plus some coefficient multiplied by the variable is equal to 0. Differential equations of these kind of form, they have solutions that contain simple harmonic oscillations within them. We can find out what is the solution of this kind of a differential equation by solving what is known as the determinant equation, which is k minus omega square m determinant is equal to 0. So k here is, of course, this is the matrix, m here is this. What is omega? Omega basically are the distinct frequencies which are solutions of this matrix equation. In fact, the general solution of this kind of matrix equation can be written as theta 1 t and theta 2 t is simply equal to some kind of a constant. Let's suppose I say x11, x21 e to the power I omega 1 t plus some kind of a constant x21, x22 into e to the power I omega 2 t, where omega 1 and omega 2 are the eigenvalues of this kind of a determinant equation, and this quantity is the eigenvector, and this kind of quantity is the eigenvector corresponding to omega 1 and omega 2. So our challenge is to find the eigenvalues associated with this determinant equation and their corresponding eigenvectors. Once we do that, then we can write the general solution in this kind of a fashion. All right, so let us do that. So let us first solve this determinant equation. So this determinant equation simply is nothing but k minus omega square m. All right, so k is what? G upon L plus k upon m minus omega square 1, right? So just omega square. Second, you have minus k upon m, and then you have just minus k upon m, and then lastly you have g upon L plus k upon m minus omega square into 1, that is just omega square. Determinant is equal to 0. So let us solve this to obtain the eigenvalues of this kind of a system. So this will give us g upon L plus k upon m minus omega square multiplied by g upon L plus k upon m minus omega square, minus this becomes minus k upon m whole square is equal to 0, right? This is quite easy. So the square, this minus term vanishes, and then we are reduced with an expression that looks like a square minus b square. It can be written as a plus b into a minus b, right? So this is nothing but g upon L plus k upon m minus omega square minus k upon m. This is the first term, and then you have g upon L plus k upon m minus omega square plus k upon m. This is the second term. So from here I'll get two solutions, as you can guess. So this is g upon L plus 2k upon m minus omega square. Sorry, no, this is not plus 2k upon m. This gets cancelled, right? In the first expression, these two gets cancelled. So this is 0. Okay. And in the second term, you have g upon L plus 2k upon m minus omega square is equal to 0. So finally, you end up getting the solution g upon L minus omega square is equal to 0 and g upon L plus 2k upon m minus omega square is equal to 0. So finally, omega square is equal to g upon L from the first expression, and omega square is equal to g upon L plus 2k upon m from the second expression. So the eigenvalues are omega is equal to root over g upon L and root over g upon L plus 2k upon m. So these are the eigenvalues of this determinant equation, and they correspond to what is known as normal frequencies. Now I'm going to come to that probably by the end of the video, where I'll show you that the general solution is actually a linear combination of two distinct frequencies, and these are those two distinct frequencies. Omega is equal to root over g upon L is one distinct frequency, and omega is equal to root over g upon L plus 2k upon m is another distinct frequency. And I will make you visualize how these frequencies manifest each other. But to do that, we need to obtain the general solution, and to obtain the general solution, we also need to obtain the eigenvectors corresponding to these frequencies. So let's suppose this is omega 1, and let's suppose this is omega 2. So corresponding to these normal frequencies or eigenvalues, we want to find out the eigenvector corresponding to, let's suppose, omega 1 first. So how do we do that? Well, we take the characteristic equation k minus omega 1 square m in matrix form, and then you have some kind of a vector here x, which gives you 0. All right, so let me write down the entire system. So k was g upon L plus k upon m minus omega 1 square, right? K was g upon L plus k upon m minus omega 1 square. So omega 1 square is just g upon L. The second term was minus k upon m, and the third term was minus k upon m, if I remember correctly. Yes, and the fourth term is g upon L plus k upon m, g upon L plus k upon m minus omega square. So minus omega square 1 is just g upon L. All right, that's it. Quite easy. So g upon L gets cancelled here. And let's suppose the eigenvector is something x11, x21. And on the right hand side, you have 0, 0. So this simply gives us, or k upon m minus k upon m minus k upon m and k upon m is this matrix. And then you have the eigenvector x11, x21 is equal to 0, 0, right? So if I take k upon m out of this equation, this simply becomes k upon m 1 minus 1 minus 1 1, and you have x11, x21 is equal to 0, 0. If I'm interested in finding out what is the relationship between x11 and x21, what I can do is I can reduce this first matrix. So to reduce this first matrix, what I'll do is I'll add the row 1 with row 2 and I'll substitute that in row 2. All right, so if I do this, of course k upon m goes to the right hand side, it gets vanishes. And if I do this, the first row is still 1 minus 1, but the second row is 1 minus 1 and minus 1 plus 1. So it becomes 0, right? So this simply becomes 0. So if this becomes 0, so this is essentially, these two terms are 0. So therefore, now it's easy for me to find out the relationship between x11 and x21. So x11 minus x21 comes out to be 0. So from here I get x11 is equal to x21. So therefore, corresponding to the omega 1, one of the eigenvectors is simply nothing but, if x11 is 1, then x21 is also 1. So this is the eigenvector corresponding to omega 1 is equal to root over g upon L. That's it. Now let's also find the eigenvector corresponding to omega 2. So with respect to omega 2, I can do the same thing, that is k minus omega square m, and then you have some kind of an eigenvector is 0, 0, right? What was k? K was nothing but g upon L plus k upon m minus omega square m, which is just omega square because m, the term in the m is 1, right? So what is omega 2 here? So omega 2 square is root over g upon L plus 2k upon m. So here I have to write minus g upon L minus 2k upon m. In the second term you have minus k upon m. In the third term you have minus k upon m. And in the last you have same g upon L plus k upon m minus omega square m. So omega 2 is root over g upon L plus 2k upon m, and m is 1. So that is minus g upon L minus 2k upon m. That's it. So and the eigenvectors, let's suppose x21 and x22, this gives us 0, 0. So let's quickly solve this. Here g upon L gets cancelled, g upon L gets cancelled, and you are left with this equation where you have minus k upon m here, minus k upon m here, minus k upon m here, and minus k upon m here. This is just too easy, man. I'm sure that you're following what's happening because this is just extremely simple. So from here what we can do is just take the k upon m out of it, or rather minus k upon m out of it, and you have 1, 1, 1, 1, and then you have x21, x22 is equal to 0, 0. What I want to do is I'm going to reduce the row of this particular matrix. So what I'm going to do is I'm going to subtract R2 from R1, and then I'm going to substitute it in R2. So if I do this, minus k upon m vanishes, you have 1, 1 here, and you have 1 minus 1 and 1 minus 1. That's it. x21, x22 is equal to 0, 0. So this gets cancelled out and you are left with a 0 here. This simplifies our problem in finding the eigenvectors. What do we get from here? From here we get x21 plus x22 is equal to 0, or x21 is equal to minus x22. That is, we have finally come up with the eigenvector corresponding to omega 2 is equal to root over g upon L plus 2k upon m. So the eigenvector is, if x21 is 1, then x22 is minus 1. That's it. So we have solved for the eigenvalues and the eigenvector. So this is the first eigenvector for omega 1 and this is the second eigenvector for omega 2. Now we can use these to write the general solution for these two equations of motion written in the compact matrix form. So this is the look of the general solution in terms of omega 1, omega 2 and in terms of the eigenvector. So let us write the general solution of these two equations of motion using the eigenvalues and vectors that we just now obtained. So the general solution of theta 1 and theta 2 can be written as the eigenvector corresponding to omega 1 is 1, 1, e to the power I omega 1t, and the eigenvector corresponding to omega 2 is 1 minus 1 e to the power I omega 2t. Now of course then we need to multiply this with some kind of a constant here, because we don't necessarily know what the value of these constants are until and unless we apply some kind of an initial conditions. Now if you take a look at this expression, there is an I here, and I is an imaginary number, so exponential to the power I you might be familiar with. Exponential to the power ix is simply equal to cos x plus I sin x, right? So there is a real component and an imaginary component here. We are interested in the real component. So to get the general solution that we can physically visualize here, what we must do is we must find out the real component of this entire system. Okay, so let us look at the real components in this system, the real components of this entire system. Okay, so the real components, you'll only get the cos x term. So this is nothing but c1 1 1, you will get cos omega 1t, and c2 you have 1 minus 1 cos omega 2t. Thus we can finally write down the solutions for theta 1t, which is equal to c1 cos omega 1t plus c2 cos omega 2t, and theta 2, which is equal to c1 cos omega 1t minus c2 cos omega 2t. Now c1 and c2, these are some kind of constants that will depend upon the initial setup of the coupled pendulum, but the general solution of both the two masses of the coupled pendulum and their angular displacements is given by these two expressions. So we have finally obtained the general solution for the angular displacements of both the masses in the coupled pendulum system. Now the interesting thing about the nature of the motion that we are going to look at physically also is that the general solution is a linear combination of two distinct frequencies. What is omega 1 and omega 2 here? Omega 1 is simply a frequency g upon L, right? And what is omega 2? Omega 2 is another frequency g upon L plus 2k upon m. We obtain these, right? We obtain these here. Omega 1 and omega 2 are the eigenvalues of the determinate equation, and they are two distinct frequencies. Now what you are getting is that you are getting the linear combination of two distinct frequencies. So what you have as a general solution for the first mass, right? This is for the first mass and this is for the second mass. What you have as a general solution is not simple harmonic oscillations, but rather the linear combination of two distinct simple harmonic oscillations. So there are two distinct simple harmonic oscillations hidden within the general solution of both mass m1 and m2. But what is interesting about this whole thing is that the nature of the motion of the entire coupled oscillation of the coupled pendulum is such that the angular displacements of both the masses have two distinct frequencies hidden within them. Now this has a huge significance in terms of coupled oscillators in general, but before we talk about those things, let us first visually look at the general motion of this kind of a system. So here I have a program that I've created to solve the equations of motion of a coupled pendulum using some kind of a numerical computational method in Scilab. So what I'm going to do is I'm going to give the system some kind of an initial displacement. So let's suppose I give the first mass 10 degrees displacement and I'm give the second mass -5 degrees displacement. If I run this, I should get the nature of its general solution. Okay. So the nature of its general solution, yes. The first graph represents the θ1, the angular displacement of first mass with respect to time, and the second graph represents θ2, that is the angular displacement of the second mass with respect to time. Now, of course, you can see a lot of oscillations. You can also see that the amplitude of the oscillations are varying. You can also see that when the amplitude of the first mass decreases, the amplitude of the second mass keeps on increasing. Now, this is a very interesting kind of a behavior. To appreciate this behavior further, let me take a very specific kind of an initial condition. So what I'm going to do is, let me say that the second pendulum is at rest. Okay, so the initial displacement of the second mass is 0 degrees. So I only give some finite displacement to the first pendulum, 10 degrees. Now, if I run the simulation, what I end up getting is, come on. Yes, beautiful. So here you see for the first mass, the angular displacement initially was how much? 10 degrees. So of course here the y-axis is in radians, right? And then it starts oscillating back and forth. But for the second mass, the initial displacement is 0 degrees. Initially, it was not displaced at all, but because it is connected to the first mass, it starts oscillating. But the manner in which it happens is that the first mass, it oscillates, but the amplitude keeps on decreasing. The second mass, it starts oscillating and its amplitude keeps on increasing. Slowly, the amplitude of the first mass approaches 0 as the amplitude of the second mass increases, becomes maximum. After some time, the amplitude of the second mass decreases and the amplitude of the first mass increases. So both these two pendula keep on oscillating in such a manner that the amplitude of one keeps on increasing, the others keeps on decreasing, the amplitude of the other keeps on increasing, and the first one keeps on decreasing. Let me show this to you via a simulation. So here we have this kind of a coupled pendulum system. I'm giving, let's suppose, -10 degrees to the first pendulum and 0 degrees to the second pendulum. Here you have the graph for the first pendulum and the graph for the second pendulum. If I start the simulation, you see the first pendulum initially keeps on oscillating, but its amplitude keeps on decreasing. The second pendulum's amplitude keeps on increasing. And a point comes when the second pendulum's amplitude is maximum and the amplitude of the first pendulum is minimum. And then again, the amplitude of the second pendulum decreases and the amplitude of the first pendulum keeps on increasing. So what is happening is that both the pendulums are exchanging energy. You see, initially the first pendulum is oscillating and it loses energy, and the second pendulum gains that energy and starts oscillating and its amplitude increases. After some time, the second pendulum loses energy and the first pendulum gains its energy and it keeps on oscillating with increasing amplitude. The behavior is beautiful. It's a very, very interesting behavior. The second pendulum is oscillating, right? Now slowly the first pendulum starts oscillating and the second slowly comes to rest. And the first pendulum has maximum amplitude. Now it starts decreasing and the second one starts oscillating. Its amplitude starts increasing, and on this keeps on happening. Beautiful, isn't it? Absolutely beautiful. All right. So this beautiful motion of the interaction between two pendulum via some kind of a spring mass system manifests in this kind of a manner. Okay, so coming back to our calculations, the general solution is a linear combination of two distinct frequencies, right? Now I want to show you something interesting. As you can see from the general solution, the first is of course the variation of the first pendulum with respect to time, right? And the second is of course the variation of the second pendulum with respect to time. As one's amplitude decreases, the other's amplitude increases. Now what I want to show you is that as you see from the graph, there is oscillations happening, right? It is oscillation happening. What is the nature of this oscillation? And you also see that there is an oscillation of this nature, the modulation. What is the nature of this oscillation? Is it equal to omega 1 and omega 2? or is it something else? So to do that, first of all, let me choose the initial conditions for which these graphs are true. That is, at time t is equal to 0, let's suppose the theta 1 at time t is equal to 0 had some angle theta naught. I took 10 degrees, remember? And the theta 2 at time t is equal to 0 is, let's suppose, 0. And theta 1 dot is 0. I'm not giving it any kind of a velocity initially at time t is equal to 0. And I'm also not giving any velocity to the second pendulum at time t is equal to 0. I'm only giving it some kind of a displacement to the first pendulum. That is all. If I do this, then the general solution becomes a particular solution of this. So at time t is equal to 0, theta 1 is theta 1 naught is equal to c1 cos 0 plus c2 cos 0. And at time t is equal to 0, theta 2 is 0 is equal to c1 cos 0 minus c2 cos 0. Since cos 0 is equal to 1, right? From here I can say that c1 plus c2 is equal to theta naught plus, but c1 minus c2 is equal to 0, which simply means that c1 is equal to c2, or I find that c1 is equal to c2 is equal to theta naught upon 2. That means I can write these two general solutions that I've obtained for the case of when I give the first pendulum initial displacement of theta naught in this manner, that theta 1 at time t is simply equal to theta naught upon 2 cos omega 1 t plus cos omega 2 t. This is the first solution. And theta 2 t is equal to theta naught upon 2 cos omega 1 t minus cos omega 2 t after substituting the values of constants that I've obtained in this equation. This is the nature of the particular solution when we only displace one of the pendulum by some kind of an angle. Now, what is my objective? My objective is to figure out how omega 1 and omega 2 are related to these oscillations. Right. So for that, I'm going to do a little bit of a substitution here. So what I'm going to say is that omega 1 is equal to half of twice of omega 1. So which is equal to half of omega 1 plus omega 2 plus omega 1 minus omega 2. All right. And I'm going to say that omega 2 is equal to half of twice of omega 2. Why I'm doing this, you'll understand in just a moment. Half of omega 2 plus omega 1 minus omega 1 plus omega 2. So this can simply be written as, what is this? This is equal to omega 2 plus omega 1 upon 2 minus omega 2 minus omega 1 upon 2. And this is equal to omega 2 plus omega 1 upon 2 minus, or rather plus omega 2 minus omega 1 upon 2. So if I write these two solutions in this manner, okay, so if I write the solution for theta 1 in terms of this quantities, omega 2 plus omega 1 upon 2, omega 2 minus omega 1 upon 2, then this simply becomes theta 1 t is equal to theta naught upon 2, you have cos omega 1 t. So omega 1 is what? Omega 1 is equal to omega 2 plus omega 1 upon 2 minus omega 2 minus 1 upon 2 t, right? And then you have omega 2. What is omega 2 here? Omega 2 is this. So this is nothing but omega 2 plus omega 1 upon 2 plus omega 2 minus omega 1 upon 2. Now, using a trigonometric identities of cos A plus B, this can be written as theta naught upon 2. So what is the first term? This is cos A minus B. So cos A minus B can be written as cos A, which is omega 2 plus omega 1 upon 2, cos B, so which is omega 2 minus 2 minus omega 1 upon 2, plus sine A, which is omega 2 plus omega 1 upon 2 sine B. Similarly, the second term becomes cos A plus B, which is equal to cos A cos B minus sine A sine B. Now what happens here is that these two terms are same, so they get cancelled out, and finally I end up getting this is equal to twice of theta naught by 2. So this is theta naught cos omega 2 plus omega 1 upon 2 and cos omega 2 minus omega 1 upon 2. So I have finally obtain the expression. So this expression, this general solution, theta naught upon 2 cos omega 1 plus omega 2t, can simply be written in this particular fashion. Now what is this? This is equal to theta naught cos some kind of a frequency omega 1 plus omega 2 upon t. Let's suppose that is delta. There is a t here, okay? There's a t here, t here, t here, t here, t here, t here, and here. So there is a t here and there is a t here. So let's suppose this is delta t and this is cos gamma t, okay? So delta here is omega 2 plus omega 1 by 2 and gamma here is omega 2 minus omega 1 by 2. Now what are these? That is what I wanted to show you, that if you look at the general solution for theta 1, there is this oscillation, right? This oscillation that is happening, right? The frequency of this oscillation is actually this particular frequency, omega 1 plus omega 2. And there is another oscillation that is happening, this oscillation, the oscillation at which the amplitudes are increasing and decreasing, right? And the oscillation of the frequency associated with that is the gamma here, which is omega 2 minus omega 1 by t. So the frequencies that you see here are not omega 1 and omega 2 separately, but rather the frequency of this oscillation is omega 1 plus omega 2 upon 2, and the frequency of this modulation is omega 2 minus omega 1 upon 2. So what you end up having is, you end up having these oscillations whose amplitudes are modulated by a further oscillation. You have these oscillations whose amplitudes are modulated by a further oscillation. So this is a kind of a modulated wave where you have these oscillations, but these amplitudes are modulated by a further oscillation. And the oscillations are happening at a frequency of omega 1 plus omega 2 upon 2, and the modulation is happening at a frequency of omega 2 minus omega 1 upon 2, because the general solution of the first theta 1 can be written in this manner. Isn't it interesting? Similarly, I can show the same thing for the second case. So you have these oscillations which are happening with a frequency of omega 1 plus omega 2 upon 2, and they are modulated by another frequency of omega 2 minus omega 1 upon 2. Now, can we also physically visualize these distinct frequencies omega 1 and omega 2 separately? Well, yes, we can do that. We can physically visualize these distinct frequencies omega 1 and omega 2 separately, and that brings me to the last topic, which is normal modes. So using these general solutions, which are linear combinations of omega 1 and omega 2, I want to create a setup where I will either have omega 1 or we'll have omega 2, so that we can physically visualize them. For that, I'm going to give you two special conditions or two special cases. The first special case is when the theta 1 at time t is equal to 0 is, let's suppose, some angle theta naught, let's suppose 10 degrees or 15 degrees, and theta 2 at time t is equal to 0 is also the same angle theta naught. And I'm going to give you another special case where theta 1 at time t is equal to 0 is equal to some small angle theta naught, let's suppose 10 degrees, and theta 2 at time t is equal to 0 is minus theta naught. You will see that under these two special conditions, the entire system is going to execute SHM. So you can figure it out by applying at the time t is equal to 0 condition from here and the time t is equal to condition from here. So at time t is equal to 0, you have theta naught is equal to C1 cos 0 plus C2 cos 0, and you have theta naught is equal to C1 cos 0 minus C2 cos 0. Here on the other hand, at time t is equal to 0, you have theta naught is equal to C1 cos 0 plus C2 cos 0, and theta naught is equal to, or minus theta naught is equal to C1 cos 0 minus C2 cos 0. If you solve it, if you solve both these two, you will find out that theta naught is equal to C1 plus C2 and theta naught is equal to C1 minus C2 simply leads to C1 is equal to theta naught and C2 is equal to 0. While on the other hand, here theta naught is equal to C1 plus C2 and minus theta naught is equal to C1 minus C2 simply leads to C1 is equal to 0 and C2 is equal to theta naught. Thus, if C2 is 0 in this case and C1 is 0 in this case, the solution becomes theta 1 is simply equal to theta naught cos omega 1t and theta 2 is simply equal to theta naught cos omega 1t. That means both the systems are executing SHM with a frequency of omega 1, while on the other hand, you have for C1 is equal to 0, you get theta 1 is equal to theta naught cos omega 2t and theta 2 comes out to be minus theta naught cos omega 2t. Both of these systems are executing SHM, although they are out of phase by 180 degrees. These configurations, when a coupled oscillator oscillates as SHM or executes simple harmonic motion, are known as normal mode. So this is known as the first normal mode, and this is known as the second normal mode. And these normal modes can only be found out when we give the same displacement for the first situation and exactly opposite displacements in the second situation. So let's run the simulation and see what we get. So here I give the first pendulum a displacement of minus 10 initially, and the second pendulum also a displacement of minus 10 initially. And if I run it, what do you get? You get simple harmonic oscillations. Both the pendulums are executing simple harmonic oscillations in phase with one another. Both of them are executing simple harmonic oscillations with a frequency of omega 1 in phase with one another. The inner spring system is uncompressed. So under these initial conditions, when both the initial displacements are exactly equal, the entire system oscillates in SHM. So this coupled oscillator, whose general solution is not an SHM, but we can figure out some specific initial conditions in which it does execute SHM, and this is known as the first normal mode. However, if I make the angles opposite one another, let's suppose I give initial displacement of minus 10 degrees to the first pendulum and initial displacement of 10 degrees to the second pendulum, and then I run it, then you see that the entire system is executing SHM but out of phase. In fact, 180 degrees out of phase. So as the pendulums are approach together, they go away, approach together, go away, approach together, go away. The entire system and the masses of the system are executing SHM, as you can see from the graph here, but they are 180 degrees out of phase. This happens when we provide theta naught and minus theta naught to the initial conditions. And this is therefore known as the second normal mode. So in the first normal mode, the entire system executes SHM with a frequency of omega 1, which is equal to G upon L. There is no K term here because the spring inside is uncompressed, as both the pendulum are oscillating in phase with the same amplitude. While on the other hand, these pendulums are oscillating with the same frequency but 180 degree out of phase. Therefore, the angular frequency here is omega 2 is equal to G upon L plus 2K upon M that we have obtained. Here the spring is involved. So normal mode is that configuration in which the entire system is executing SHM with distinct frequency, and these frequencies are known as normal frequencies. The interesting thing about these frequencies is that the general solution of the coupled oscillator, which is the coupled pendulum here, is a linear combination of these distinct normal frequencies. So as you can see in the coupled pendulum problem, you have these normal frequencies, which are these distinct simple harmonic oscillations hidden within the general solution, and the normal modes are those in which the entire system starts executing SHM with respect to those frequencies. So that is all for today. Let me do a very quick revision. For the coupled pendulum system, first we obtained the kinetic energy, then we obtained the potential energy, then we obtained the Lagrangian, and we also applied the small angular approximations. Using that, we got this expression of a Lagrangian, which we applied to the Euler-Lagrange equation for theta 1 and theta 2 respectively to obtain the equations of motion, which are nothing but two second order differential equations in terms of theta 1 and theta 2 that needs to be solved simultaneously. So therefore I wrote them in a compact matrix form whose general solution is of this nature. To solve this, to obtain the general solution, we need to find out the eigenvalues and eigenvectors corresponding to omega 1 and omega 2. For that, we solve the determinant equation. From here, we got omega 1 and omega 2. These are in fact the normal frequencies. And we also obtain the eigenvectors, and using the eigenvectors and the eigenvalues, I represent the final solution, the general solution of the coupled pendulum. And we saw that for specific situations when I give initial displacement to only one pendulum, the entire system starts oscillating and those amplitudes get modulated by another oscillation, which is given by this particular diagram. We can also look at omega 1 and omega 2 separately by looking at the normal modes corresponding to these normal frequencies. So that is all for today. I hope you enjoyed studying the interesting behavior of the motion of a coupled pendulum system. I'll see you in the next lecture. Thank you very much.